Okay, in 8 and 9, in the last two parts of the chapter, we're going to talk about polymers and the types of solids that polymers make, and then we're going to talk about nanomaterials. We're going to kind of deal with the weirder stuff here at the end of the chapter, things we haven't talked about before. So, talk about polymers. Polymers are just molecular solids that are formed by what's called polymerization, okay, which means you're joining together monomers. And monomers are just one big long chain. That's all that means. I'm taking one monomer or one small chain of carbons, usually is what it is, and you're adding it to another one and another one and another one kind of deal. Take these big, what's called polymers, okay? So polymers are usually plastics, and when we deal with plastics, we deal with polymers. And there are 3 different types of plastics here that this book talks about, and we're going to talk about. The first one is the thermoplastic, which is one that can be reshaped, melted down, and reused. There's a thermosetting plastic, which you shape, but it can't be reshaped because however you got to make its shape is an irreversible reaction and you can't undo it. And then you have what are called elastomers. And elastomers are rubbery or elastic behavior type plastics. These are ones that if you stretch or apply a force to in some way will then retain the original shape once that force leaves, like a rubber band. Okay, you can stretch it to whatever you want, but then when you're done stretching it or applying that force, it goes back to what it should be originally. So there are types of plastics and they're kind of overall types of polymer there. All right, now we're going to talk about how you make polymers, and there are 2 ways to make polymers. All right, you're either doing addition polymerization or doing condensation polymerization. Okay, addition is just what it sounds like. You're taking monomers and you're coupling them or adding them. Well, how you couple them is through multiple bonds opening up. So we have these multiple bonds in between the carbon atoms here. Okay, and in between those carbon atoms, all right, those electron pairs open up, and one electron goes there, one electron kind of goes there, one comes here, one goes there, and you end up making the bond in between. That's why you get that polyethylene there on the right. That's an addition. Nothing was taken out. All you did was you rearrange the electrons, kind of like a resonance structure kind of idea. All right. If you have a condensation polymerization, that's where you have 2 or more that join together to form a larger molecule, and you eliminate a smaller molecule. Okay, so if we have the polymerization, all right, and the example here is this bottom one. All right, you're making this long polymer with an N and a C double bond or a carbonyl group. Okay, and what's happening is you're getting rid of a water because this N and that C are going to bond together. So you start off with these 2 things here. All right, and then we're going to get rid of that portion there, all right, and you end up, oops, sorry, one of the red ones, not the white ones. You're going to get rid of that portion, okay, and now I have a water molecule and they're going to be stuck together. So condensation is what it sounds like. You're condensing it, all right, I'm getting rid of something, I'm putting 2 things together to condense what you had just had before, okay. Now we'll look at some properties of polymers, okay. The big thing is that they're very flexible. Okay, because they're single carbon-carbon bonds. So they're really easy to move because there's no pi bonds there that are holding them in their certain shape. Okay, both synthetic and natural polymers consist of big macromolecules, what they're called, macromolecules, macro meaning large, okay, of different weights. So a synthetic polymer is one that they had to make up in the lab, and there are some natural polymers that have been around for, centuries, that are actually just big long chains themselves. You don't have to actually make them up. All right. There are some different types of polymers, okay, and that's how they deal with recycling based on what kind of polymer it is. So you see like the numbers in the bottom of bottles for like PET or HDPE or something like that, where the ones that can be promoted or ones that can be recycled and ones that can't be. All right. You have polypropylene, high density polyethylene, polyvinyl chloride, or PVC. PVC is a big one for pipes. Okay, those are the different types. There are some different examples. All right, most are amorphous solids, meaning again they soften over a range of temperatures. Okay, they're very slow because they have no crystalline structure. Their crystallinity kind of goes along with the amorphous solids. Something's crystallinity is the extent of the ordering of a polymer. More ordered or harder ones, usually they're more dense, usually they're more heat resistant because they have more of an order to them. So some polymers are more amorphous than others. Some have a higher crystallinity, some are a little bit less crystallinity, a little less crystallinity, and a little more amorphous. Okay, Lower density ones tend to be lower crystallinity, a little less organized, okay? You can actually make them a lot stiffer by having bonds between two different chains, and that's called a cross-linking. And that's what we're going to look at over here. This right here, it's not a very great picture, but in the book it's a little bit better. Because if you have these big chains, these little things right here are what link a couple of different chains together. You're linking this one and this one together. That's cross-linking. That makes those a little bit more rigid. Okay. In the picture on the left here is actually talking about crystallinity. These are a little more ordered sections. These are a little less ordered section. That has a higher crystallinity. That one has a lower crystallinity. Okay, and this is going to be a higher density. Here's just more ordered. There's more stuff there in that particular region. Okay, so that's kind of dealing with all about polymers. All right, now we're going to look at nanomaterials. Okay, when we talk about nanomaterials, the weird thing with these is like talking about a very small molecule. Okay, very small scale for us. All right. And they progressively change as your molecule is made larger or smaller. So you have some weird different changes that we're not going to get into about when you have these small materials. Okay, photoluminescence is something kind of crazy. You can actually illuminate them with UV light, and the solution will actually emit light that corresponds to whatever the band gap is. So that's why things photoluminesce, or sometimes why things phosphoresce, depending on what you're dealing with. But they'll luminesce a certain amount of light or a certain kind of light depending on what the band gap is between two things. And that's that gap between your bonding and your anti-bonding. Okay, we talked about that. We talked about nanomaterials and metals. It's kind of crazy when you have really finely divided metals. It'll actually change colors. If you put gold in molten glass, especially to make a stained glass window, that's going to make the stained glass window red. So gold is not normally red, but when you actually finely divide it and make a really fine powder and put it in molten glass, it actually will make that glass red. So it's kind of neat when you have these really small, really finely divided particles. Okay. The last thing we're going to look at here are graphite, graphene, and what's called a fullerene. So basically we're looking at carbon. Okay. Up until 1985, carbon was only thought to have only been the forms of diamond and graphite. Okay. It came along after 1985 that you actually have what was called a Buckminster Fullerene, because it's somebody's last name, okay? And that was C60. And that's here is actually C60. It looks kind of like a soccer ball, okay? They're now known as just fullerenes, and the smallest fullerene you can actually have is C20. C20 and C60 just means how many carbon atoms there are in that arrangement, okay? If you have what's called a carbon nanotube, that's when you have sheets of graphite or sheets of carbon that are actually rolled up. So these right here are examples of carbon nanotubes, okay? You spin these into different fibers and polymers, and it makes them a lot tougher. So when I talk about composite softball bats, because I deal with softball, so composite things for that, that's a carbon mixture, usually with some kind of polymer, all right? And you're adding that carbon to it in the form of usually a nanotube or a graphite or graphene, okay? Graphite and graphene are a little bit different. Graphene is actually just one layer of graphite, okay? And it actually wasn't until 2004 that they realized that there's actually one long layer. You can have a single layer of carbons, okay? And be flat, which is two-dimensional. This is 2D. It's a flat sheet of carbon, and they're all carbon atoms. They're very actually slippery because the carbon atoms actually move past one another actually fairly easily. Because you have one layer moving around with another layer, okay, which is why graphite is actually very, in pencils, it's actually very soft and very slippery. That deals with this carbon or graphene layer, and this graphene layer can slide, okay. They're a honeycomb, what they call a honeycomb structure, okay. It's a very, very, very strong material. It's actually the strongest material ever recorded, okay, and the electrons can actually travel long distances without meeting another one. So that's a very high, what they call thermal conductivity, or high conductivity, because the electron can very easily pass from one end to the other and not run into anything else. So graphite and graphene are kind of crazy. When we talk about them, they're basically just carbon, nothing else.